Okay, moving on in section 4.4, concavity. Now we want to talk about what's a point of inflection. So this is sort of similar to we had a critical points. Critical points were where the first derivative is equal to zero. Now a point where the graph of a function has a tangent line and where the concavity changes is what's called a point of inflection. And what is a point of inflection? Well, the second derivative is equal to zero, or the second derivative doesn't exist. It's just like a critical point was where the first derivative is equal to zero, or the first derivative failed to exist. And a point of inflection is where the second derivative equals zero, or it fails to exist. But a point of inflection is where the function could possibly change its concavity. Just because we have a second derivative equals zero doesn't require that. But at a point of inflection, where the function changes its concavity, you definitely have to have the second derivative equal to zero or not existing. So, how do we use this? Okay, so for example, let's say in example 63 here, let's look at y equals x to the fourth. So here's a picture of y equals x to the fourth. So visually we can tell that we have a concave up curve everywhere. Notice that if I take the derivative, I get 4x cubed. Then if I take the second derivative, I get 12x squared. So the second derivative, I set that equal to 0, so we have x equals 0. However, that x equals 0 is not a point of inflection because the concavity of this function does not change. The concavity is always up. This is always a concave up function, holds water everywhere. So x equals 0, even though the second derivative is 0 there, is not a point of inflection. Now let's look at y equals x to the 1/3. So notice that y equals x to the 1/3, the first derivative is 1/3, x to the minus 2/3, and so the second derivative is minus 2/9, x to the minus 5/3, or that would be minus 2 over 9 times x to the 5/3 in the denominator. Okay, so the second derivative, there's no place where it's 0, but it doesn't exist when x equals 0 because I'm dividing by 0. And notice that we do have a change of inflection here, or a change of concavity. We have concave up from minus infinity to 0, but then at x equals 0, even though the derivative doesn't exist, the function does, we have a change in concavity. So it changes from concave up from minus infinity to 0 to concave down from 0 to infinity. Water would spill right out of that. Okay, so that means that x equals 0 is a point of inflection, and it wasn't where the second derivative is 0, it was where the second derivative doesn't exist, but either one of those could be a point of inflection.